So in this problem, we're given some information about the initial and final state of a gas, and we're asked to compute some thermodynamic properties and some differences, in this case, difference in enthalpy and entropy for this gas. And this is basically a review of as far as we've gone in thermodynamics in this class for the purposes of considering compressible flow. So to start with, we'll look at uh, part A. So we want to know T1. In this case, we're going to be using our ideal gas law. So we're going to say P1 is equal to rho 1 R T1. That is the formula we're using in class. In this case, um, we know P1, we know rho 1, and we're trying to find T1. So we'll say T1 um, is going to be equal to P1 rho 1 R. We have to find R. It's not given in the problem statement, but we are told that we're considering argon. So if we go to table A4, we'll see that for argon, we're going to get an R of 208 in SI units, right? So it's meters squared per second squared Kelvin, and we're in SI units down here. So we can plug this all in. So this will be 1.7 times 10 to the 6th over 18 times 208. And that works out to T1 is equal to 454 Kelvin. So now we need to find the final density. So this is rho 2. And again, it follows as before. So we have P2 is equal to rho 2 times RT2. Therefore, rho 2 is equal to P2 over RT2. That's equal to 248. This is kilopascals, so it's 248 times 10 to the third over 208 times T2 is 400 Kelvin. And so therefore, we'll get rho 2 is equal to 2.98 kilograms per meter cubed. So that was our those are our properties of the gas, initial properties of the gas. And then now we want to find the change in enthalpy, first of all, right? So now we want to find H2 minus H1. And in this case, we're going to use our CP, and we know that we can estimate CP as KR over K minus 1. So we know R, we've looked that up for table A4, but let's go in here and find RK, or our specific heat ratio, in this case 1.67. So this is 1.67 times 208 over 1.67 times 1 equal to 519. K is unitless, so this is going to have the same dimensions, in this case units, as our gas constant. So this will be meters squared per second squared K Kelvin. And so now we can find H2 minus H1 is equal to CP times T2 minus T1 equals 519 times T2 is given as 400K. We computed T1 as 454. So we're going to have H2 minus H1 is equal to negative, or roughly negative 28,000 joules per kilogram. Great. So now for part D, now we're asked to find the change in entropy of the gas through this process. So now we have S2 minus S1, and we know that we can find this as S2 minus S1. So if we derive this for a perfect gas in class, S2 minus S1, Cp natural log of T2 over T1 minus R natural log of P2 over P1. So this is going to be, we have everything here. This is going to be 519 natural log of 400 over 454 minus 208 natural log of, let's see, P2, um, what, 248 kilopascals divided by P1 is 1.7 megapascals. So we could write this as natural log of, let's write it. So 248 times 10 to the third over 1.7 times 10 to the sixth. Therefore, we get S2 minus S1 is equal to about 334 meter squared per second squared Kelvin. So that's just really a brief review of sort of as far as we've gone with thermodynamics in this class, just so we can solve some introductory problems in compressible flow. Obviously, things can get much more complicated for for real fluids, but this is also a good reminder that oftentimes in a compressible flow problem, we might not be given everything about the fluid, but you shouldn't forget your thermodynamic state relationships. So, for example, if I were to then ask you something like the speed of sound at this initial condition, condition one, you know that we can, or you should know that we can find that speed of sound based on the temperature. But since temperature was not known, you have to compute it, and we can compute it using the ideal gas law. Okay, so this is really just a reminder, a review of our thermo, but also a good reminder to not forget this small amount of thermodynamics that we've introduced in order to solve problems in compressible flow. All right, thanks again.